Biochemical reactions. This segment of the tutorial will introduce biochemical reactions, including their thermodynamics, the concept of coupled reactions, and the enzymes in biochemical reactions. First law of thermodynamics. The total energy of a system and its surroundings is constant. Energy cannot be created or destroyed. Energy can take different forms, however: heat, light, etc. For instance, the work in turning this crank can make this light bulb glow. Second law of thermodynamics. The total entropy of a system plus its surroundings always increases. Water molecules are highly ordered when in ice. It has low entropy. Notice how organized these water molecules are. When the ice melts, the water molecules become more disordered, and this is an increase in entropy. When water turns to steam, a kind of gas, entropy is at its maximum. Notice no order. Entropy. Entropy is denoted by the letter S, and entropy is the measure of the degree of randomness or disorder in a system. The second law of thermodynamics says that the total entropy of a system plus that of its surroundings always increases. A local increase in order will only occur if entropy in another part of the universe is decreased in an equal or greater amount. Water. As water goes to ice, the water has a decrease in entropy. There is an increase in order in the ice. However, there's a decrease in order in another part of its universe. Entropy comparison. Entropy and matter comparison. Less, more entropy. Solid has less entropy than a liquid. A liquid has less entropy than a gas. A solute and a solvent separated has less entropy than in solution. A small, simple molecule has less entropy than a large, complex molecule. And less molecules have less entropy than more molecules, which have more entropy. Delta G versus reactions. Delta G, which is kcals per mole or kilojoules per mole, is the change in free energy. A spontaneous reaction. A naturally occurring reaction that once started will continue to happen without outside intervention. The delta G is negative in a spontaneous reaction. Non-spontaneous reaction is an unnatural process that after it is started will not continue to happen without outside intervention. A non-spontaneous process only happens when outside action introduces energy to drive the process. Delta G is positive in a non-spontaneous reaction. Coupled metabolic reactions. Let's look at the equation. A goes to B plus C. B then goes to D. The delta G is described by this equation. Delta G prime plus RT times the natural log of the products of the concentration of C times D divided by A times B. Notice those square brackets. That always refers to the concentration. The overall free energy change for the coupled reactions is equal to the sum of the free energy of the individual steps. If delta G is negative, the reactions can be spontaneous. Delta G naught is the standard free energy change. And this is the products over the reactants. Let's look at the reaction in terms of delta G. A goes to B plus C, resulting in a positive delta G of 21 kilojoules per mole. B going to D has a delta G of a negative 34 kilojoules per mole. When these are summed, the total reaction of A going to C plus D has a net negative delta G of minus 13 kilojoules per mole. This is an example of a coupled reaction, and most of the reactions and metabolic processes in a living cell are coupled in this fashion. Glycolysis coupled reactions. Glucose going to glucose 6-phosphate. A phosphate group has been added to the glucose molecules, shown here with the orange atoms. ATP is hydrolyzed to ADP. The first reaction in glycolysis is making glucose 6-phosphate from glucose. The hydrolysis of ATP to ADP provides the energy by thermodynamic coupling. Notice the delta G equals negative 31 kilojoules per mole. Let's look at the reaction. ATP plus H2O goes to ADP plus inorganic phosphate with a negative delta G of 31 kilojoules per mole. Inorganic phosphate plus glucose goes to glucose 6-phosphate plus water. That has a positive delta G of plus 14 kilojoules per mole. The net energy change is a negative delta G of 17 kilojoules per mole. This is a coupled reaction, ATP plus glucose going to glucose 6-phosphate plus ADP. The net reaction is a negative delta G, so this will go spontaneously. Enzymes affect the rate, not the equilibrium. Enzymes are catalysts. Enzymes do not alter the equilibrium of a chemical reaction. Enzymes only affect the rate of a product formation, not the amount. On this axis we have the product. On this one we have time. Enzymes accelerate the rate of the reaction. This is the rate of product formation with the presence of an enzyme. This is the rate of the product formation in the absence of an enzyme. Given an infinite amount of time, both the enzyme plus reaction and the enzyme minus reaction would have the same concentration of products to reactants in an infinite amount of time. Activation energy E sub A. Enzymes lower the activation energy necessary for a reaction. On this axis, we see energy plotted against the reaction coordinate, that is, how far the reaction has proceeded. Let's look at the reactants. This is the transition state without enzyme. Notice how high the energy required is. Uncatalyzed reaction, no enzyme. Notice how low the transition state is for the enzyme catalyzed reaction. The activation energy with no catalyst. Notice this is the difference between the enzyme catalyzed reaction and the non-enzyme catalyzed reaction. Notice the difference in the energy states and how much energy is required to get to the activation energy. This is the lowered activation energy. Biochemical reactions. Types. Oxidation reduction. Group transfer. AX plus B goes to A plus BX. Group transfer. Formation of an ester-thiol ester amide bond. Isomerization reaction, transformation of a molecule into a different isomer. Hydrolysis, ester, ethers, amides. A plus water goes to X plus Y. Elimination addition reactions. Two substituents are removed from a molecule. An example is 2R-OH going to ROR plus water. Elimination reaction. Enzyme reactions. There are 6 classes or types of enzyme catalyzed reactions. Class 1, oxidoreductases. These perform oxidation reduction reactions. Class 2, transferases. Transferases transfer specific groups. Class 3, hydrolases. They catalyze hydrolysis reactions. Class 4, lyases. Catalyze chemical bond breaking of various types other than hydrolysis and oxidation. Class 5, isomerases. Catalyze the interconversion of polymers. And Class 6, ligases. They catalyze the joining of two molecules by forming a new chemical bond.